Hi everyone, we're going to do a quick video on seasons. This is also the last part of chapter 2. So we have looked at all the ways to transfer energy in chapter 2, and that included kinetic energy, potential energy, and also the different ways of transferring it. Now we're going to talk about seasons because seasons are a result of some of those transfers of energy. That's what we're going to go through now. Just to sum up heat transfer and what you've done up until now, you have looked at the air being heated by the surface of the earth. The air is not heated by the sun. The air is heated by the conduction in the first few inches of from the surface to about 6 to 7 inches above the surface of the earth. And then convection moves parcels of that air up into the upper atmosphere where warm air rises. And then in the upper atmosphere, the sun can warm that thin atmosphere up there. So to put it all in perspective, the ground warms the lower atmosphere, the troposphere, where we have 95% of our weather, or all of our weather. The ground heats the troposphere, and the warmer the ground is, the warmer the air will be in the troposphere. Now let's talk about what that warm air has to do with seasons and why we have seasons. It seems a little strange that if you think about the physical act of the earth circling the sun, it doesn't seem to go with seasons. But energy transfer actually does, and I want to show to you why the physical act of transferring the sun doesn't really correlate with the seasons. In July, right now, we are actually farthest away from the sun by quite a bit, by 5 million miles. We're farther away from the sun than we are in January. And not only that, but in July, when we're farthest away from the sun, our northern hemisphere is tilted so that we get the maximum impact of the sun. Kind of strange. And then you come around in January and the southern hemisphere has the maximum impact of the sun. They have summer in January, but their Januaries, when they are closest to the sun, when the earth is closest to the sun, their Januaries in the southern hemisphere are cooler than our summers when we're farthest away from the atmosphere. So what's going on there? What really drives our seasons? And actually, our seasons are driven by two things. One is the angle of attack of the sun. And we just talked about the fact that in January, the southern hemisphere is getting the full beam of the sun. This particular slide shows the June in the northern hemisphere, where the northern hemisphere gets the direct rays of the sun, and the southern hemisphere gets the indirect rays of the sun, so that it also feeds into winter now during our summer months down in the southern hemisphere. So this beam of light is like taking a flashlight and holding it at an angle where the beam scatters and it's not as intense, versus, on like Law and Order, when you see the cops go in and they hold the flashlight right next to their eyes and they direct the beam of the flashlight right by their eyes. And that's a direct beam, much like in the summertime when we have a direct line or a perpendicular line for the sun in the northern hemisphere during the summer, right? So the angle of attack has a lot to do with the amount of energy that's transferred to the earth. And in addition to that, there are the number of daylight hours, which really impact the amount of energy that's transferred to the Earth's surface. So for instance, let's go back to the June solstice that we were talking about. When the northern hemisphere gets a more direct line of the sun, and this is at 40 degrees Celsius. So you can see a really direct line here. Look at 40 degrees Celsius here. a lot more of an angle to the sun along the surface of the earth. Not nearly as direct as it is here at 40 degrees Celsius. And we get 15 hours of sunlight on June 21st. And that is opposed to the southern hemisphere, where at the 40-degree mark, they get 9 hours of sunlight. So you can't transfer as much energy with less time in the sun. Those are part of the two reasons, the angle of attack and the amount of time that is associated with the sun in that area. On the equinox, strangely enough, there's equal time for the sun, 12 hours, all the way across the globe. From the North Pole straight to the South Pole, every place on Earth at the equinoxes gets equal sunlight and equal nighttime. It's a really amazing day. Equinox stands for equal night, equinox. And those are the equinoxes that happen in the spring with the March equinox and at the fall, September equinox. And you will have exactly 12 hours of sunlight and daylight on those days. So two reasons why we have seasons, and they both are related to energy transfer. In another way, and we have talked about the axis a bit, but I want to talk about the axis a little bit more. Our axis generally is at 23.5 degrees, and that axis points to one star in the galaxy, and that axis really does not change. We'll go into a little bit of a wobble, and we'll go into that later when we talk about climate change. But basically, our axis is maintained throughout the elliptical order of our rotation. Our rotation around the sun is not a circle. It's more of an oval, an ellipsis, and it's an ellipsis on an angle. So as a result of that, there are some seasonal differences to how the sun looks in our sky. What I did here is this is a drawing out of your book, and I flipped the drawings so that they are a little bit easier for you to understand. I have north up at the top and south down at the bottom. I'm looking at the North Pole, at New Jersey, and at the equator. Let's start with what you know in New Jersey. If we look at New Jersey, what we're seeing here is that we know that in December, the sun seems low in the sky. It's usually circling, and we look for the sun in the southern part of the sky, and it seems low on an angle when we are looking at the sky during the winter solstice. By the equinox in March, the sun has moved higher in the sky, and this is all due to the angle that we were talking about and the rotation. And by June, the sun is quite high in the sky, and it reaches its peak on June 21st for how high it is in the sky. If we were looking at the North Pole instead, what you would find is that the sun does not set in June. There's 24 hours of daylight in June, and the sun is very low in the sky at the equinox. At the December solstice, at the winter solstice, there is no sun at the North Pole at all. So you can imagine there's not much transfer of energy up there during the winter time up at the North Pole. And at the equator, everything doesn't change very much at the equator. The sun is quite high in the sky at the equinox. It's right directly above you at the equinox of the equator. The sun tends to vary to the north a bit in June and to the south a bit in December, but it's not anything that you'll really find is dramatic at the equator. The equator basically gets 12 hours of sunlight all year long. A lot of sunlight and a lot of transfer of energy at that time. This is a picture of the June 21st solstice, the summer solstice, up at the Arctic Circle, and the fact that the sun never sets in 24 hours at the solstice. So it's called the land of the midnight sun. The sun will go low at midnight. then it'll pick up and it'll stay very low in the sky for 24 hours. So I thought you'd find that beautiful to see. It is really lovely. And I wanted to go over just a second for here. The summer solstice, generally June 21st, can vary a day or two. In the northern hemisphere where we are, the sun at noon is directly overhead, and the days are greater than 12 hours. In fact, our day is 15 hours and 6 minutes at the summer solstice. The autumn equinox, September 22nd, it's a great day. 12 hours of sunlight, 12 hours of nighttime throughout the world. And the winter equinox is our shortest day of the year, generally around a 9-hour day on December 21st. It's part of the reason we have all of the religious celebrations that involve light. The Hanukkah celebrations, the Christmas celebrations all involve lights because they were looking at the winter solstice and trying to provide light to the world and holidays in that time. The spring equinox, the vernal equinox, March 20th, again, same 12-hour daylight and nighttime throughout the entire world. At the North Pole on that date, finally, the sun rises again. The North Pole had been in darkness from the autumn equinox, and then the sun finally rises 6 months later at the spring equinox. You can imagine that there are many celebrations around the Arctic Circle at the spring equinox. In New Jersey, the differences in these seasons means that we get stronger, longer sun in the summer. Obviously, we get weaker, shorter sunshine in the winter. And our longest day of the year is not our warmest day of the year. And conversely, our shortest day of the year is not our coldest day of the year. And that is also related to transfer of energy and temperature lapses. And we're going to go into the specific heat of water and air in the coming chapters. So I am looking forward to that. Hope you enjoyed this. See you on the other side.